Good morning, everyone. We're starting a new chapter today here on AP Calculus, and the chapter we are going to be looking at is Chapter 10, which is probably the chapter that most people hear about is really rough as far as Calculus BC goes. It's a chapter on sequences and series, series in particular. And all of that may be true for a lot of people, but the thing you really need to understand is that the major part of your AP Calculus grade, your AP Calculus test score, I should say, is going to be dependent on how you do on this section. There really isn't a whole lot on AP Calculus BC that's different than AB, and this is one of those major things. So as Chapter 10 goes, so goes your AP Calculus BC score. So that in mind, let's keep positive, and we'll get going with this, and we'll get you off to a really good start. So we've got this. The framework here is going to be hidden figures, and I say that, but it's more about the space exploration, and Hidden Figures is just such a great movie because it frames a lot of the stuff that we do in Chapter 10 in a kind of historical wrapper. So if you don't know it, Hidden Figures is a 2016 American biographical drama film loosely based on the nonfiction book of the same name by Margot Lee Shetterly about black female mathematicians who worked with NASA during the space race in the 50s and 60s. The film stars Taraji Henson as Katherine Johnson, the mathematician who calculated flight trajectories for Project Mercury and other missions. The film also features Octavia Spencer as NASA supervisor mathematician Dorothy Vaughan and Janelle Monáe as NASA engineer Mary Jackson. In 1961, Catherine worked as a human computer. Now, that's not a job description you hear very often, but this was a really, really, really big thing not so long ago. So she worked as a human computer in the West Area Computers Division of Langley Research in Hampton, Virginia, alongside of her colleagues, Mary Jackson, and their unofficial acting supervisor, Dorothy Vaughan. They're all African-American women, and the unit is segregated by race and sex. And so the thing you think about is that, the scientists of the day, they were the ones who got all the glory, but they didn't do a lot of the computation. When we say human computer, what we're saying is that she was a person who did all the computations for the NASA scientists. They didn't have to do any logarithms on their own unless they really wanted to. They would just kick it down to the West Area Computer Division and have one of these women do all of their calculations for them, because there were no computers in the way that we think about them anyways, or even computers, period, at the early part of this story. The term computer, in use from the early 17th century, the first known written use dates to 1613, meant a person who computes, a person performing mathematical calculations before electronic computers were commercially available. Many of the rules of mathematics, and this is the important thing to think about, many of those rules of mathematics that we think, why do we do this? Or the origin is it made calculation by computer a lot easier. So we do a lot of these things like simplify logarithms, etc. We do them because it makes things easier for a person to compute, for a computer to calculate. I think the easiest one to see is, well, why do we rationalize a denominator on fractions? And you got to think it's a lot easier to divide by 2 than it is to divide by the square root of 2. And if you don't believe me, go ahead and grab your pencil and paper and try to do 5 divided by square root of 2. Let me know how far you get. It's a lot easier to do 5 square root of 2, 5 multiplied by the square root of 2, and then divide that entire thing by 2. So division in particular is a lot easier if you rationalize the denominator. It's not just some random rule. Anyways, that's just context here. And before we can start, we need to define the very topic of the next few weeks. It is infinite series. So an infinite series takes the form of, basically, it's a sequence added together. This particular sequence has an infinite number of terms. Sorry, this particular series has an infinite number of terms, but that doesn't have to be the case. This part over here, we read the sum as k goes from 1 to infinity. I think you see the 1 to infinity of ak. The numbers a1, a2, a3, etc. Those are the terms of the series, and an, we call that the fifth term. Generally speaking, we're going to be going from 1 to infinity. If that changes, I will definitely let you know. Next, we have a partial sum. The partial sum only adds a few of the series, a few terms from the series. So S1 is just the first term. S2 is terms 1 and 2, and S5 would be the first 5 terms, etc., etc. And our first thought here is that if we have the sequence of partial sums, if that sequence has a limit, then the series is said to converge to that limit. So if everything that we add up together, if we add an infinite number of terms, if that sum approaches a number, then that number, the limit, is said to be S, and we say that the infinite series converges to S. If the infinite series doesn't converge, then the series is said to diverge. Important for you right now is that you don't get caught up in this whole sequence of partial sums. That's something which we're not really going to do in order to assess whether a series converges or not. You just need to know that if the partial sums do converge to a limit, if they do have a limit, then the series itself is said to converge. So let's write the first 4 terms of this series, and then we'll write the first 4 partial sums, and then we'll just say, hey, do we think this series converges? Okay, we usually think, or we can think of the series kind of like function notation. So we're going to substitute 1, and the first term is going to be, let's see, if I substitute a 1, I get 2 plus 1 over 1 plus 1. That's 3 halves. Okay. The first sum then is just 3 halves. Now the second term, we're going to substitute a 2 into this general formula here, and we'll get 2 plus 2 over 2 plus 1. So that's 4/3. And if I add those first 2 terms together, we're calling that S2. So S2 is going to be 3 halves plus 4/3. That is what, 9 plus 8. That's 17 over 6. Maybe, to assess these limits, we're going to go ahead and put these as decimals. So 17 over 3 is about 2.83. Okay, moving on. The third term, that's going to be 2 plus 3 over 3 plus 1. So that's 5 over 4. And our S3, our partial sum number 3, that's going to be the first 3 terms added together. So 3 halves plus 4/3 plus 5 over 4. That's equal to 98 over 24. And that approximates to, what is that, 6.08? And finally, the fourth term of this sequence, it's a sequence. The fourth term of the series, I guess, that's going to be 2 plus 4 over 4 plus 1. What is that? 6 over 5, 6/5. And that makes the fourth sum, the sum of the first four terms. So 3/2 plus 4/3 plus 5/4. And that adds up to, and whoops, plus 6 over 5. And that is approximately, well, it's exactly equal to 317 over 60. And that is approximately equal to 5.28. So let's take a look here. We got 1.5 as our first. Actually, before we get into that, I'm going to also note that I was really dumb here, because if I take a look at this, I should have seen the sequence of the numerator, 3, 4, 5, 6, over the sequence of the denominator, 2, 3, 4, 5. So without even doing any calculations, you should be able to figure out that A5 is going to be 7 over 6. So look out for that. Taking a look now at the partial sums, our first partial sum is 1/5. Why the heck did I say 1/5? 1.5. Our second partial sum is 2.83. Our third partial sum is 6.08. Our next partial sum is 5.28. And, the rate of increase here, I don't know if you can see or not. Is that decreasing? Well, it kind of increased from here to here, and then it decreased a little bit. So it's kind of hard to tell. But in all actuality, this limit, as n approaches infinity, of the partial sums, that doesn't exist. So this series doesn't converge, which is a great way of saying that the series diverges. So the next part, and this is kind of major for us, it's that if the series is going to converge, then each of the individual terms need to trend toward 0. And why do we think that's true? Well, let's take a look at series AK as an example. And let's say the terms don't approach 0. So we'll say let's say that they approach 3. So we've got 1 plus 2 plus 2.5 plus 2.6 plus, let's make that 2.7 plus, et cetera, et cetera. Okay. At some point, this has got to be about equal to, or approximately equal to, 3 plus 3 plus 3 plus 3. Because the limit as n approaches infinity of I said k, right? That was going to be equal to 3. So at some point, we're just going to be adding 3 a whole bunch of times. And if that's true, then, there's no way that this sum can converge, because if we add 3 a bunch of times, well, we're just going to get a more and more increasing number. Okay. So if the sum just keeps increasing by 3, then it's not going to converge. But let's take a look at this sum Bn, okay? And let's say that these terms do approach 0. So we're going to start with, let's start with 1, and then we'll go to, 1/4, and then we'll go to 1/8, and then we'll go to 1/16, etc., etc., etc. Okay, so eventually, at some point, we're going to be adding numbers close to 0. Plus 0, plus 0, plus 0, plus 0. Not exactly equal to 0, but a number that's really close to 0. So we can see the what happens here is the influence of these first few terms is very strong, because as we get to the end here, we're basically adding nothing to the sum. We said that was B. So the sum effectively stops increasing. I don't know why I put a caret there. I've got a computer. The sum doesn't actually stop increasing, but it stops increasing by an appreciable amount. So the little bits that we add to the sum are so small that they don't really make a difference anymore. And so in this case, we're saying that, the series might converge. Maybe it doesn't, but it at least has a chance of converging. This statement makes the most sense in that we can now rule out a whole bunch of series that won't converge just by checking to see if the limit of the individual terms is 0. And that's what we're saying here. If the series converges, then the limit of all of the individual terms has to approach 0. However, the converse is not always true, which would be as saying if the limit of the individual terms approaches 0, then maybe the series converges. It's not 100% that series is going to converge. So if the limit actually, I just kind of rewrote this over here. If the limit of the individual terms approaches 0, then the series may or may not converge. Maybe it'll converge. And then we go right away into this, probably the biggest seeming paradox of series is that we have this thing called the harmonic series, which is a series as n goes from 1 to infinity. It can start anywhere, actually, of 1 over n. Okay. This series famously does not converge. And you're going to want to really remember that, because this is going to come up over and over again in your studies. The harmonic series is not a series that converges. And what this means, or one way that I really like thinking about this, is if I add enough terms of the harmonic series, I can get a sum bigger than any value that you could think of. Okay, so if I wanted to make this bigger than 5, I'm going to need a few terms, but I can make this sum bigger than 5. And if I wanted to say 90, it's going to take a lot of terms, but this sum will eventually be greater than 90. And if I wanted to do, 200, I'll need a heck of a lot of terms, but this harmonic series will eventually be sum up to a number that's greater than 200. So this harmonic series does not converge. It'll get as big as you need it to get. You may need a few million terms, but it'll get there. Okay, let's pretend we're aiming a NASA telescope and we need to make a series of adjustments in the telescope angle. Let's say we position our telescope 5 degrees down from vertical, so S1 is equal to 5. The next angle will be the previous angle plus half of the previous correction. So S1 is going to be equal to 5. S2 is going to be 5 plus half of 5. S3 is going to be 5 plus half of 5 plus half of 5 again. So how do we do this? Well, can we write S7? And we're going to want to use exponents. So let's take a look at our pattern. S1 or S7 is going to be the first term, 5, plus the second term, which is 5 multiplied by 1/2, plus that third term, which is 5 multiplied by 1/2 multiplied by 1/2. So 5 multiplied by 1/2 squared. And then from these first three terms, maybe we can get a pattern. So here's term 1. We'll say this is n equals 1. This is n equals 2. This is n equals 3. And to illustrate what's going on here, we're going to fill in a couple of blanks. So this first term may just be 5, but we can think of this as 5 times 1/2 to the 0 power. And the second term here, that's 5 times 1/2, but we can think of this as 5 times 1/2 to the first power. Now, if we take a look at how the index of each term is related to the power of 1/2, I think we could see the power, the rule here. So the fourth term is going to be 5 times 1/2 to the third power. The fifth one, n5, that's going to be 5 multiplied by 1/2 to the fourth power, and then 5 multiplied by 1/2 to the fifth power, and then 5 multiplied by 1/2 to the sixth power. So this is the way S7 works, and it just kind of illustrates that sometimes when you simplify, you're not seeing the complete picture. So with series especially, simplifying might work against you in a lot of cases. Taking a look at this, getting ahead of myself. The series that we just wrote here is a series that's called a geometric series. And in a geometric series, we have a first term multiplied by a common ratio, is what we call it, over and over again. So if we look at the series that we just wrote out, we kept on multiplying by 1/2. So the second term is the first term multiplied by 1/2. The third term is the second term multiplied by 1/2. The fourth term is the third term multiplied by 1/2, etc., etc. So we can write this series in a sigma notation because what was our first term? First term A was equal to 5. And then the common ratio, with the thing that we kept multiplying by, that was 1/2. So since we recognize this as a geometric series, we can say that the series is going to be equal to the summation of a r to the n minus 1, which, substituting those numbers, we get 5 multiplied by 1/2 to the n minus 1 power. So that's how we write this geometric series. Geometric series is kind of related to the geometric sequence because you can see how each of these terms of the series actually forms a geometric sequence. So the sum of a geometric sequence is called a geometric series. Now, I don't know where you're coming from with your pre-calculus and your Algebra 2 skills, but this part is actually from the Algebra 2 curriculum here, where I teach. But the geometric series is only going to converge if the absolute value of r is less than 1. If the geometric series has an r, absolute value of r that's not less than 1, so greater than equal to 1, then the series is going to diverge. Also, if the geometric series does converge, we know that it's going to converge to a over 1 minus r. These two little bits of information about geometric series are extremely important. They're both really important. I can't really stress to you how important these two things are because, without them, the rest of this chapter is going to fall apart for you. So really take a note of this, put a few stars next to it, put a highlighter around it. Incredibly important. So does the angle of the telescope converge? And if it converges, to what angle does it converge? Just to remind you, the function for that angle, or the series for that angle, was 5 multiplied by 1/2 to the n minus 1 power. Analysis of that sigma notation tells you that a is 5 and r is 1/2. And the really important part here is the 1/2, the radius. No, I'm sorry, the ratio. Because if the absolute value of the ratio, which is the absolute value of 1/2, is less than 1, well then that series is going to converge. And of course, the absolute value of 1/2 is less than 1. So this series does converge. And that series is going to converge to a over 1 minus r. Substituting things into there, we get 5 over 1 minus 1/2. But you've got to simplify 5 over 1 minus 1/2 because this is a fraction inside of a fraction. And you got to simplify those. In any case, that simplifies to 10, so this series will converge to 10. Okay, so strap in, because this is where things are going to get really interesting. What if we want to make a function to describe a variety of angles and corrections? We're going to start off with a basic function, which is a geometric sequence with a equals 1 and r equals x. So the ratio that we're using is a variable. That's the interesting part here. So look what we do here. We've got a over 1 minus r is the same thing as a1 over 1 minus x, which is the same thing as 1 plus x squared plus x cubed. Now, if we call the sum f of x, then what we're really saying is that f of x is equal to 1 over 1 minus x, which equals 1 plus x cubed plus etc., etc. And then we get to x to the n minus 1 power plus even more things. This little bit right here that we wrote, it just kind of tells you what the form of the next term is going to be. We call this a general term, and it's the same thing as whatever we would put in the sigma notation. So in this case, 1x to the n minus 1, which is the same thing as x to the n minus 1. Because this is just a because this is just a geometric series, it's going to converge to the sum, which is 1 over 1 minus x, if and only if the absolute value of r, which is the absolute value of x, is less than 1. We can rewrite that absolute value of x less than 1 in a couple of different ways. We can write it as negative 1 is less than x is less than 1. Or we can write it in set notation where x is a member of the set of real numbers between negative 1 and 1 open. All three of these notations give us the same set of numbers for which the series is going to converge. Because of that, we call these three things the interval of convergence. Now, you only need to write it using one of these three notations. Most of the time, higher math classes are going to favor that third set notation where we have x epsilon negative 1 to 1. That's generally favored in higher math classes. So this interval of convergence, just like the name says, it's going to give an interval for which the series is going to converge. Also important here is we just made a function which is a series, an infinite series really. So f of x the function of f of x can be defined not only in regular notation as 1 over 1 minus x, but we can also define it by this geometric series 1 plus x plus 1 plus x squared, etc., etc. Functions that are formed by series or can be formed by a series are called power series. Basically, we've taken a series and we've made it into a function, and that function is generally called a power series. Now, power series can be written as the sum of a constant multiplied by x minus a to the n power. As you can see in this highlighted thing, we have the series of cn x minus a to the n, and that's equal to c naught plus c1 times x minus a plus c2 times x minus a squared, etc., etc. That's the way all power series can be written. We call this number a the center of the series, and we call it that because a is always going to be in the center of the interval of convergence. So in that first example we did, where we have the absolute value of x is less than 1, a is equal to 0, which means a is the center of this series. Notice how that's true regardless of the way we write the interval. Between negative 1 and 1, the center of that interval is 0. So a is the center of the interval also in this form. And then, of course, that's also going to be true with x as a member of the set between negative 1 and 1. 0 is the center of that set of numbers. So things get kind of confusing here because now we have a and we're calling a the center, whereas before a was the first term of a geometric series. So I'm going to try to circumvent that confusion a lot by just referring to a in the power series sense as the center of the series. Let's get into some power series questions. And our first one is find the power series for 1 over 1 plus x and find the interval of convergence. If I compare 1 over 1 plus x to a over 1 minus r, I can see that they would be the same thing if I let a equal 1 and I let r equal negative x. And that's kind of the key here, is we want to equate it with the sum of a geometric series and then figure out what does a need to be and what does r need to be to make this whole thing work. So we've got 1 over 1 plus x equals 1 plus negative x plus negative x squared plus negative x cubed, which is the same thing as a plus ar plus ar squared plus ar cubed, by the way. So for all of these power series, you basically want to rewrite them so that the only thing, well, no, let's just say that so that inside the power, so for example, inside negative, whatever is being cubed, I just want that to be x minus a number, or x plus a number, because that's a pretty easy conversion, but x minus a number. And here I have negative x to the cubed. That's not x minus a number. To make this work, we're always going to make the simplification where, for example, negative x squared, that's the same thing as negative 1 squared multiplied by x squared. Also, I'm seeing it in the future, but if we have something like 3x, the whole thing squared, that's the same thing as 3 squared multiplied by x squared. So we're always going to want to unlock the x part from this ratio. So this simplifies our series into 1 plus negative 1x plus negative 1 squared x squared plus negative 1 cubed x cubed plus, and then all the way down to negative 1 to the n, x to the n. Well, now we can just simplify those negative 1 powers, and that gives us the very elegant series 1 minus x plus x squared minus x cubed plus negative 1 to the n, x to the n. So that's kind of like an alternating power series for a geometric series. Now for the interval of convergence, we're going to make our absolute value of our ratio, which is equal to the absolute value of negative x, which doesn't take a lot of simplification to see that that's the same thing as the absolute value of x, and that needs to be less than 1. We've already met this interval of convergence before, so I'm just going to write it negative 1 to 1 in set notation. And that takes care of this first problem. It's a long one, right? Now taking note of problem number 2, x over 1 plus x, you can actually kind of shortcut things just a little bit here if you're clever with your algebra. Because x over 1 plus x is the same thing as x multiplied by the quantity of 1 plus x. And we already have a series for 1 over 1 plus x. So we'll just substitute that series right in there for that sum, and then we'll distribute our x, and there's a series. For the absolute value, for the interval of convergence, r is going to be the same thing, or r is still negative x, and we've already worked on r equals negative x. So we know the interval of convergence is x, absolute value of x is less than 1, or in set notation, x is between negative 1 and 1. For our last question here, we've got 3 over 1 minus 2x. So we can't really tweak either number 1 or number 2 to fit and make 3 over 1 minus 2x. So we'll start over from the beginning again, and we'll equate that with the general, or the sum of any geometric sequence. Okay, this inequality is only going to hold true if a is equal to 3 and r is equal to 2x. So that's enough for me to make my series. Just like before, we've got 2x to a power, so we're going to want to separate out so we have only x with the power. Okay, so we've separated out all of our 2's, and you'll notice that I left this as 3 times 2 squared, 3 times 2 cubed, 3 times 2 to the n. And in chapter 10, when we're dealing a series, it's not really necessary for you to multiply everything out. In fact, under most circumstances, it's probably better for you if you don't multiply things out, because the pattern will be easier to see. So I'm just going to leave it like this. If you really want to substitute and say 3 times 2 cubed is, 24? Go right ahead and do that. But remember, that's just one more basic arithmetic step where you could make a mistake. And if you make a simple mistake, like 3 times 2 cubed is equal to 12 instead of 24, you're really in for it, because you've just turned your 5 into a 4 because you don't know how to multiply. So I wouldn't take that risk. There's nothing wrong with 3 times 2 cubed. For the interval of convergence, we know that the absolute value of the ratio 2x has to be less than 1. And that doesn't look like the form of x minus the center is less than the radius. So we're going to have to do something here to simplify that. And I think the problem is that there's a 2 multiplying the x here, and there's nothing multiplying the x here. So we'll just multiply both sides by 1/2. That gives me the absolute value of x is less than 1/2, which means x is between negative 1/2 and 1/2, or x is a member of the set from negative 1/2 to 1/2. Here in our important ideas, we've met all of these, and so we're just gonna go through this briefly. So we've got the general form of a geometric series, a over 1 minus r, and again, I'm gonna explain to you how important this is. We've got the power series. A power series is any series with a variable like x in it. And if we call A the center of the series and we say that any value C is a constant, then every power series can be written in the form of C0 plus C1 x minus a to the first power plus C2 x minus a to the second power, etc., etc. Which brings us to the interval of convergence, which is a major part of this chapter. So the interval of convergence is an interval of x, where as long as you let the value of x be in that interval, the series is going to converge to whatever the sum is or whatever function you say it converges to. For a geometric series in particular, there are some definite rules about convergence. So for a geometric series, the absolute value of r has to be less than 1. And in order to find the interval of convergence, you need to solve this so that you get a inequality of the form x minus the center is less than the radius. From there, you can either write your interval of convergence as center minus radius to center plus radius, either in an inequality or in set notation. Okay, this brings us to our check your understanding here. Do the following series converge or diverge? And if it does converge, give the sum. Looking at this first question, we've got 1 plus 2/5 plus 2/5 squared plus 2/5 cubed. Now, a major part of how well you do here is going to be locked up in your ability to recognize that you are looking at a geometric sequence. A geometric series. You can tell because to get from one term to the next, we just keep multiplying by 2/5. So this is a geometric series. The first term is 1, and the ratio is 2/5. Because this is a geometric series, we know a lot about when it converges and when it doesn't converge. For this series to converge, the absolute value of the ratio needs to be less than 1. So the absolute value of 2/5 has to be less than 1, and wouldn't you know it, the absolute value of 2/5 is less than 1. So this series converges. The series converges to 1 over 1 minus 2/5. Now you can't leave that because you have a fraction inside of a fraction, so you need to simplify that. And that just simplifies to 5/3. For question B, if I take a look at this and I compare it, I basically write it next to the general term or the general formula for a geometric series, I can see pretty quickly that this is a geometric series with a equals 2 and r equal to 1/3. That means the absolute value of r is equal to the absolute value of 1/3, which is of course less than 1. So this series does converge, and it converges to 2 over 1 minus 1/3. Like letter A, we can't leave this because we have a fraction inside of a fraction, so we got to simplify that, and that simplifies to 3. Now for question 2, we have find the interval of convergence. Find the interval convergence of the function of x represented by the power series. And we don't really have a whole lot of things to go on here, so these better all be geometric series. So if it doesn't look like a geometric series, like letter A, then what you should do is write out the first 4 terms of the series. I highly recommend that if you get something in sigma notation like you have here, write out the first 4 terms, and then you'll be better equipped to see if it is a geometric series. So not even bothering to simplify this a whole lot, we can see that this is geometric because our ratio is equal to 3x. we keep multiplying by 3x. Is also, I can get the first term is going to be equal to 1. So this geometric series is going to be equal to 1 over 1 minus 3x when the absolute value of 3x is less than 1. Now that doesn't look like absolute value of x minus a is less than a radius, so we're going to have to solve here. And we did this previously. I'm just going to divide everything by 3. So we get the absolute value of x is less than 1/3. And if you think about this, this is the same thing as the absolute value of x minus 0 is less than 1/3. So this gives us our radius or our interval of convergence. So x needs to be between negative 1/3, or maybe I should say 0 plus negative 1/3 and 0 plus positive 1/3, which is another way of saying x must be between negative 1/3 and positive 1/3. Letter B, we're going to implement kind of the same strategy. We'll write out the first 4 terms again. And it looks as though we keep multiplying each term by negative 1 x minus 2. So this series converges to 1 over 1 minus negative 1 x plus 2. We can simplify that, and it simplifies to 1 over x plus 3. The absolute value of the ratio is the absolute value of negative 1 multiplied by x plus 2, which is equivalent to the absolute value of x plus 2, which needs to be less than 1. Now this already looks like of the form of x minus the center is less than the radius. So the center here, we're going to call that negative 2, and then the radius, we're going to call that 1. This gives me the interval. X must be between negative 3 and negative 1, which we can also write in interval notation, x between negative 3 and negative 1. So hey, that was a really long one. I'm looking at the time, and it's pretty much an entire class period. So yeah, not a whole lot to say other than good luck. Really take the things that I've highlighted and memorize them well. And we'll see you next time.